shall we start?
Yeah, let me just introduce you. So welcome back, everyone. We have this is the third part of a three-part series of lectures by Sudip Ghosh, and he's been giving a wonderful series of lectures on celestial holography and scattering amplitudes on the celestial sphere. And so this is part three. Sudip, go ahead.
Okay, so thanks guys for tuning in again. Okay, so this is actually sort of the last set of things which I wanted to talk about. But let's sort of actually recap. Let's do a quick recap of what we said since it has been a couple of weeks. So let's refresh our memory of what we did. So basically, what we did essentially was that we wanted to see scattering amplitudes in sort of a new light, and the reason was that we wanted to make the underlying sort of actually yeah so uh, yeah so yeah yeah, so in that case we saw that basic. Okay, let me actually open this first page, it's easier. Yeah, so as we said that basically in this case we know that the action of the Lorentz group is basically equivalent to the action of the conformal group in actually one lower dimension. So therefore we expected just from a group theoretic point of view that is that if you write down some four-dimensional S matrix, then it has to do something with, let's say, some two-dimensional CFT correlation function. And then we sort of defined how one can sort of actually make this resemblance precise by defining what are these Mellin transformed and actually kind of sort of basis of asymptotic states, in which we defined our Mellin amplitudes as follows. Let's just look at the formula once. Where it is, sorry. Yeah, yeah. So in this case, basically, we defined a new set of objects, which we called the celestial or the Mellin amplitudes, which were given by by a Mellin transform of our and actually scattering matrix elements, which were these ANs. And then the point of doing this was that the new object which we defined, this Mellin amplitude, that transformed manifestly as a 2D CFT correlation function. Okay, and there were sort of other motivations in trying to do so, because in this case, this relation between 4D scattering amplitudes and 2D CFT correlation functions is sort of a hint of holography in asymptotically flat spacetimes. And this representation of scattering amplitudes seems like a useful way to go about actually studying flat space holography. Okay, so that's what we did. We defined what this basis is. We studied its various properties. For example, how the action of the Lorentz group, or equivalently the conformal group, acts on this new basis of states. We discussed a bit about actually space-time translations, which were not completely manifest in this which were not completely manifest in this basis, which was given by Pastarsky, Shao, and by Strominger. So then I sort of motivated that you can make space-time translations manifest by going to by defining a certain modified Mellin basis, which includes in addition to whatever we had before this yes so so in this case basically that includes these u coordinates which had the interpretation of some retarded time coordinate at null infinity, right? And then using that one could define what are known as this modified Mellin amplitudes. And the salient feature of this modified Mellin amplitudes was that they made the geometric action of space-time translations completely manifest. Okay, and there were some other advantages also of this modified Mellin transform, which I briefly touched upon last time, and those had to do with the fact that this PSS Mellin transform, or basically this Pastersky-Shao-Strominger Mellin transform, so that turned out to be actually, so that turns out to be sort of actually badly behaved if you want to study, let's say, the Mellin transform of, let's say, graviton scattering amplitudes. It turns out that this Mellin transform is actually UV divergent, but this modified Mellin amplitude, which contains this exponential e to the power minus I omega u factors, so that actually regulates this divergence, and then using this modified Mellin basis, you and actually basically get some meaningful answers. Okay, so that's what we discussed, and then towards the end of last lecture the lecture last time, we also saw what happens in the case of massive particles. So all the discussion prior to that was restricted to the case of massless external particles, and we saw how things generalize to the case of actually massive external particles. So in that case also, one could write down a form of one could choose a basis and write down the scattering amplitude in a way which manifests the underlying conformal symmetry. But in this case, but in this case, the celestial amplitude took a slightly more complicated form, in the sense that in this case also there is this integral transform, but this integral transform now involves what are called this bulk to boundary propagators. Okay, so so in this case the formula becomes a bit more complicated. Okay, so so that's roughly what we have been discussing up till now. So basically today what I want to do is that I want to tell you a bit about soft theorems, and in particular how soft theorems look like when you go to this conformal basis, and then we will study some and then we will study some implications of this so-called conformal soft theorems for the operated product expansion in the celestial CFT. Okay, good. So so let's go ahead. Okay, so basically I don't need to tell you about soft theorems. I suppose you know everything about it, but just to recap, so soft theorems are basically the following statement: that suppose you have some scattering amplitude with some n+1 number of particles, and then you let's say have and then let's say you have some extra guy, which in this case could be, let's say, some graviton or some gluon or some photon, and then you take the momentum of this particle to be small. Then what turns out is that this n+1 point amplitude that basically factorizes in terms of an amplitude without the soft particle. So in this case, so in this case, basically on the right hand side we have an n point amplitude without the soft particle, and then there is some prefactor which is organized in terms of the energy of the soft particle, which is denoted by omega here, and these prefactors, which are this S0, S1, and S2. So these are basically what are known as soft factors, and depending on at which order in omega these appear. In this case, these factors have various names. So for example, the first guy, which appears as the residue of this omega equal to 0 pole, that is known as the leading soft factor. Then there is an order 0. So then there is an order 1 term that's obviously labeled the subleading soft factor. And then you can have subleading soft factors and so on. So just to show you some formulas, I guess this also all of you are actually familiar with. So for example, if you take this soft particle to be, let's say, some graviton, then these soft factors have actually various explicit expressions, which for example look like this. Okay, great. So now what we have sort of learned in this business of actually soft theorems in the last few years is that the soft theorems are actually intimately related to the so-called asymptotic symmetries of asymptotically flat spacetimes, right? So the statement which actually Strominger and collaborators and various other people have shown is that soft theorems are essentially the Ward identities for certain asymptotic symmetries. Okay, so yeah, but today what I want to do is that basically I want to so basically I want to look at this connection between soft theorems and asymptotic symmetries. I want to look at this collection. I want to look at this. I want to look at this connection through the lens of this Mellin transform. Okay. So then, what in this case will turn out is that if you do a Mellin transform, then what you can define from this from the usual momentum space soft theorems, you can define what are called conformal soft theorems, and equivalently these conformal soft theorems will so what I will show is that these conformal soft theorems can be regarded as actually Ward identities for certain infinite dimensional symmetries in the corresponding celestial CFT. Okay, so in this case, so in this case that is going to be the idea. Okay, great. Okay, great. So now what are these conformal soft theorems? So of course, when we go to this conformal basis, if you recall the definition of this conformal basis states, then we have this integral over so in this case, we have an integral with respect to the energies of the particles, right? So remember that when we were doing this Mellin transform, we had this integral of the following form: d omega, omega to the power delta minus 1, and then some factors 0 to omega. So of course, since we are integrating over all energies, we cannot simply take the usual soft limit where we sort of consider the omega going to 0 limit. So then something has to replace this notion of omega going to 0. Okay. Then it turns out that the thing which plays the role of this energetic soft limit in the conformal basis is basically the following. So so in this case, it turns out if you take these conformal dimensions, which denoted by delta, and if you take certain if you take this and if you take certain limits where this delta tends to some specific integer values, then what you can so in that case it turns out that so in that case it turns out that specific integer values of delta they are sort of the analog of the soft limits. So as I will show in a brief moment that, for example, if you take, let's say, the delta going to one limit within a Mellin amplitude, then so then from that you get what is known as the leading conformal soft limit. If you take delta going to 0, that will be termed as the subleading conformal soft limit, and so on and so forth. So now the reason this is interesting, why actually one can sensibly take this delta going to specific integer limits and extract something useful from it, is that because the celestial or Mellin amplitudes, they turn out to so it turns out that celestial or Mellin amplitudes have actually poles at the specific values of delta. Okay. So in this case what you can show is that if you start with some n plus 1 point Mellin amplitude and take, let's say, delta going to 1 in that n plus 1 point Mellin amplitude, then that amplitude is going to factorize in terms of an n point Mellin amplitude. So in this case, let's actually try to look at so in this case, let's try to look at, let's say, some quick example of it, of how that works out. So in this case, let's say consider so let's consider some generic n plus 1 point Mellin amplitude, which I have denoted as this guy here, mn plus 1, which is some function of this conformal dimensions delta, and then there are also the spins sigma and so on, and the zz bars are of course there. Okay. So that object by definition is the following thing, which is given by this integral transform of the n plus 1 point momentum space scattering amplitude. Okay. So now in this formula, so now in this integral, what you can do is that you can use a trick. What you can do is that you can insert inside this integral the following identity, which is this object. Okay. Now this identity is basically a distributional identity in the sense that it makes sense to use this identity within some integral. Okay. But now you see that the point of using this identity is the following, is that basically you see that you have these various poles in delta, right? So for example, the first term in this case has this pole at basically has this pole at the value delta equal to 1. The second term has a pole at delta equal to 0, and so on and so forth, right? So then if you insert this form, if you insert this distributional identity inside this definition of the Mellin amplitude, and then let's say take the limit where you tend this delta to 1, then what you essentially have is that you basically pick up the first term from here, right? You so in that case you basically pick up the residue of this pole at delta equal to 1, and you get some formula which looks like this. Okay.
Sorry, now, I didn't understand this argument. Can you? So you had the Mellin transform, and then why do you want to? I mean, if I insert this, then I get something else on the left hand side, right?
Yes. So in this case, So in this case, let me actually clarify. So in this case, what I wanted to do is basically the following. So say suppose I take some n plus 1 point Mellin amplitude. Okay. So then the statement which I made is that basically as you take basically, let's say delta to 1, or let's say delta to 0 or minus 1, etc. Then the point is that this Mellin amplitude is going to have some poles, okay, and we want to extract the residues at those poles, and the point is that the residue will be related to a lower point Mellin amplitude. Okay, so so basically for doing that, what you can do is that basically you can insert this identity inside the definition of the Mellin amplitude, and once you do that, so now the point is that once you insert this identity, then you can so from then what you can immediately see is that if I take, let's say, the delta going to 1 limit, then in that case the first term will be picked out, and what you will get is basically something which looks like this.
I see. Okay.
Right. Okay, good. Right.
So how do you insert this identity into the that integral?
How we insert this?
What I understood was that this integral 0 to infinity, you replace it with the theta of omega.
I have to, yes, right.
And omega to the delta minus 1, you write as 1 by omega times omega times this or something.
Yes,
right?
Yes, right.
So the theta just comes for a ride, is it?
Yeah, so in this case, basically the job of the theta function is to basically turn this integral from 0 to infinity to actually minus infinity to infinity. So basically in this case, as Anish pointed out, is this integral is from 0 to infinity. I'm going to make this minus infinity to infinity, and make this from omega to the power delta minus 1. I'm going to write it as omega to the power delta minus 2 and times an omega. Okay. And then of course with the theta function, and then I use this identity. Okay, right. So basically the point is that we end up with some object which looks like this. So now notice that we have this factor of omega times delta omega, right? So now what this does is that basically this factor will actually project out any pole that this guy has, the term within the square brackets. So in this case, if the term in the square brackets has a pole with respect to omega, So for example, if the square bracket, the term inside the square bracket gives me some term which looks like this, let's say 1 by omega, then in that case, basically this prefactor will then basically project out that pole, right? Okay, so in this case, let's try to see a specific example of how that.
Sorry, Sudip.
Yeah, go ahead.
What happens to the other terms? There are terms which are delta prime omega, right? So that also has to be taken into account, right? When you take delta going to 1.
No, so that we are not taking into account, because what we are doing is that we are just picking out the residues. Right. Yeah. So in this case, what we are doing is that we are actually neglecting the rest of the terms, and what we are doing is that we are just picking up the residues of this. Yeah. So from this object.
I see. No, I was thinking that if it is there, then you have to account for that also when you take the delta going to 1 limit. I mean, delta prime omega would then you would have to multiply by omega, and then again the next step that you did in the process.
Yeah,
I thought that would also have to be done, right?
Yeah. Oh yes. So in that case, the point is that basically what you will find is that basically this delta prime omega. So so the point is that this delta prime omega, the job of that is to project out the order 1 term in the 1 by omega expansion. So so basically what you can show is that if there is, if you are interested in just, let's say, the leading 1 by omega pole, which comes from the scattering amplitude, then the action of delta prime omega actually sets the remaining terms to 0.
I see. Okay.
Yeah.
Okay.
Yeah.
Thanks.
Good. Okay. So now let's look at a specific example of how this works out. So say suppose we take the case of, let's say, the soft graviton theorem, or what is known as the leading soft graviton theorem, which was proved by Weinberg, as all of you know. So basically the leading soft graviton theorem, so that takes so that basically takes some form like this. Okay, where this for specificity, I am considering here the soft graviton to have actually positive helicity. Okay. So in this case is S plus, so basically the notation here is the following. So I will be using this notation all throughout. So let's clarify that once and for all. So in this case, this plus basically here denotes actually the helicity of the soft graviton, which here is which in this case will be +2, and the 0 just and the subscript 0 just denotes that this is the leading actual soft factor. Okay. So as I showed before, that this soft factor is some function of the moment. Yeah, yes, go ahead.
So on the right hand side, you have an plus 1. Is that?
That's right.
Is that meant to be an?
That is meant to be an, indeed. Thank you very much.
Fine.
So that's a typo. Exactly, that's a typo. Very good. Great. Yes. Yeah. So we and that factorizes in terms of some endpoint amplitude without the soft graviton. So now what is useful to do is that you can write out this soft factor, which was some function of the momentas of the hard particles and so on, and the polarization of the soft momenta. So what you can do is that you can rewrite it using this parametrization of null momenta, which we have been using all throughout in terms of the ZZ bar coordinates. And once you do that, then you get then the soft factor basically looks like this. Okay. So these epsilons are basically some labels which can take ±1 and ±1 depending on whether the hard particles in the amplitude, in the endpoint amplitude, whether they are so in this case whether the hard particles are outgoing or incoming. Okay. So so now what we do is that basically we take this standard form of the leading soft theorem, and we basically insert it here. Okay. So then so now the point is that once we insert it, so in this case, of course, the 1 by omega pole, which is there in the leading soft theorem. So in that case, basically that is going to get actually kind of projected out, and what you will be left with is basically the following. Okay. Right. So now what you can see from here is that basically what you have is the following, is that basically from the soft theorem, what you have is that you have this, you gain some additional factors of omegas, right? And so what turns out is that, for example, when you consider, let's say, the kth term in say about this product of integrals, then in that case what you basically get is that you get a term which looks like omega k to the power delta k minus 1 and times omega k. So therefore what happens is that for the kth particle, the dimension of the corresponding conformal operator, so that basically gets shifted by a factor of 1. Okay, and so then if you rearrange this guy, then it basically turns out that you get back you basically get back an n-point Mellin amplitude where the dimension of the kth particle has been shifted by a factor of 1. Okay, so in this case what we see is basically the following, that if we start out with some n plus 1 point Mellin amplitude and take the limit where let's say we take delta goes to 1, then this object factorizes into an n point factorizes in terms of an n point Mellin amplitude, and we have some actually some soft factor as well here. So sometimes this overall factor which appears here is also referred to as the conformal soft factor. Okay, good. So now we can write out this statement in using the so now we can write out the statement using this form of this correlation function form which we had been using before. So basically, if you translate this statement about the factorization of the n plus 1 by Mellin amplitude, if we just rewrite it in terms of in the language of correlation functions, then so then in that case you basically get the following. So basically what you have is that you have some operator which I have denoted here as s plus 0 z z bar, and you have some n other, let's say, some primary operators which correspond to the n other, let's say, suppose actually particles in your original amplitude. Then such a correlation function is going to factorize in terms of an n-point correlation function. Okay, and this and so then this object or this statement about the factorization of the n plus 1 point amplitude in terms of an n point amplitude is what is basically what I will call the leading conformal soft graviton theorem. Okay, so now you may ask that what is this operator S naught? So in this case, basically this operator S naught is basically the following object, is basically the limit of delta goes to minus 1 of actually delta goes to 1 of actually the graviton operator, or in this case a soft graviton operator. And and so in this case consequently we can give it a name. We can call this object the so in this case we can call this object the leading conformal soft graviton operator. So just one more thing which I want to point out in the structure of this formula is basically this operator pk, and the job of this operator is to basically shift the dimensions of the kth operator which appears in this correlation function by factors of 1. Great. So all this I said in the standard Mellin basis, but of course you can actually carry out the same sort of, but you can carry out the same exercise in the presence of these u coordinates, or in this modified Mellin basis. And then it turns out that this conformal soft theorem, so that basically takes the following form, where now the difference in the structure is the following, that instead of this operator pk, which shifts the dimension of the kth operator by a factor of 1, you basically have this derivative operator. So in this case, you basically have this derivative operator, which is given by this del uk, and that sort of accomplishes the same objective, right? Yeah, right. So in this case, So in this case, this is the form that you get when you write it when you write down things using the modified mailing basis. Okay, so now let's try to sort of understand what this formula is telling us. Okay, so one thing which you can immediately recognize from this formula is that basically this object looks like a word identity. Okay, so in this case, basically, if you think of this object, if you think of basically this operator, or the if you think of the soft graviton operator as some current, then what this is basically saying is that basically the insertion of a current operator in some endpoint CFT correlation function is basically giving you some word identity, which is a statement about factorization of the n+1 point correlation function in terms of the endpoint correlator of the remaining primary operators. Okay. So now this word identity has to be related to some symmetries, and now we will see that this word identity is basically related to what are known as super translations. Okay, so it turns out that what you can do is that basically using this soft graviton operator, which is this s plus 0 z bar, it turns out that this is basically the generating functional for a pair of two currents, okay, which I will denote by P0 and by P minus 1. So, okay, so that happens because what you can show is that basically the leading soft graviton operator, or basically the leading conformal soft graviton operator, that can be expanded as follows, where you have two terms, in this case P0 and P minus 1. Okay. Now, for our purposes, what will be useful to do is that we can consider the modes of these operators. Okay, so in this case, you can define the modes of P0 and P minus 1 on the celestial sphere by the standard 2D CFT contour integral techniques. So yeah, so for example, you can define this object, let's say Pn comma 0 as some contour integral over, let's say, dz z to the power n plus 1 times, let's say, p0 of z. Okay, right. So now, so now what you can show is that basically if you consider, let's suppose, the modes of these operators, which I will denote as Pmn in general. So in this case, the first index here, which is m. So so in this case, this index will run over some integers, some set of integers, and the next index will denote actually which current it is. So yeah, so in this case, basically n equal to 0 will correspond to actually the modes of this operator, which is p0, and n equal to minus 1 will correspond to the modes of this operator. And what you can do is that you can go ahead and compute the algebra of these modes, and it turns out that these modes actually commute with each other. Okay, so in this case, you basically get the following trivial algebra. Okay, so now from this word identity, which we had here, what you can do if you rewrite this word identity in terms of this new set of currents, which I denoted as P0 and P minus 1, from those word identities, you can sort of extract how these modes Pmn, they act on conformal primary operators. Okay, and this is some technique which is actually very familiar from so basically in this case, also this technique is something which should be very familiar from the study of 2D CFTs. So I'm not going to go into the nitty-gritty details of that, but essentially the point is the following, is that basically if you compute the commutators of the modes of these currents Pmn with, let's say, some conformal primary operator, then in that case the commutator looks like this. Okay, so now from these commutators you can basically ask that what sort of symmetry yes, so now what you can ask is that what sort of symmetry are these objects actually implementing. and from this commutation relations with actually conformal primary operators, yes, so basically from this it is sort of immediately obvious that these objects are basically implementing infinitesimal super translations, and that is because of the fact that if you look at the geometric action of how these PMNs act on these UZZ bar coordinates, then in this case what it turns out is that the UZZ bar coordinates under the action of PMN, so they basically get translated in this case by some factor like this, right? So so from this what you recognize is that this is basically an infinitesimal version of the following statement, that U gets translated by some arbitrary function of actually Z and Z bars, and the ZZ bars, they don't change. Okay, and so that is and so that is essentially the statement of super translations. Okay, so right. So in that case,
can I ask a quick question? So
yeah, of course.
This is in your in the modified Mellin basis. This action is sort of manifest.
Yeah.
But in the Mellin basis, it doesn't seem manifest. How do I see that it is a super translation in that case?
Yeah, right. So in the standard Mellin basis, as you said, that in that case, the geometric action is not very manifest. But in that case also, the way to identify that these are super translations is to basically identify the following point. So so in this case, basically this operator, which is basically this I del del, which is basically this I del U. So the job of this operator, if you is to basically shift the dimension of your conformal primaries. Okay. So so let's write this as follows. So if you have in the modified Mellin basis an object of this form is equivalent to, in the standard Mellin basis, an object of this form, H plus half, H bar plus half, ZZ bar. Okay. So now the statement is that so now basically the statement is that whenever you see a shift of conformal dimensions of this form, then that shift is so then that shift is basically due to actually time translations. Okay,
I see.
And in this case, what we are so now if you basically actually also compute these commutators in the standard basis, then what you will get is, for example, factors like this. So this will become Z to the power m plus 1, Z bar to the power n plus 1, and then this will become H plus half and H bar plus half, right? So then what this is saying is that basically now you have a translation of this guy, but that translation is now accompanied by some factors of Z and Z bars as well. And so from that, you identify that this is basically a super translation.
I see. Okay.
Okay, good. Right. So that was the leading sort of conformal soft theorem. So next, what I want to tell you about is now what happens when you go to the next order. So then the next obvious thing to consider is the subleading conformal soft limit, which is basically the limit that so basically in this case, what you do is that basically inside an n-point Mellin amplitude, you can take the following limit. Well, let's say delta goes to 0, and then again using similar arguments from before, what you can show is that an n plus 1 point Mellin amplitude in this limit is again going to factorize in terms of an n point Mellin amplitude. So all the details of that I will and actually not go into. So for that you can look at the relevant papers where all the details are worked out. But essentially what you get at the end of the day is the following. So in this case, once again, you get so in this case also basically once again you get a factorization of some n plus 1 point correlation function in terms of an n point correlation function. right? And this also takes the form of some word identity. Okay, so in this case, where basically now in this case, basically the current operator which we are inserting is basically given now by this object. And this current operator is, for obvious reasons, known as the subleading conformal soft graviton operator. Okay, good. So now this was again in the standard Mellin basis. But what you can do is that you can, of course, translate things in in the modified Mellin basis. So in that case, your formulas become a bit lengthier because of the introduction of this time coordinates. And in this, so in that case, so in that case, the formula looks actually something like this. Okay. But one caveat which I want to point out is that basically what happened in the case of the leading conformal soft limit is that basically so in that case what happened is that basically the leading soft operator which was this S 0 plus. So it turns out that this guy has the same form irrespective of whether you write it in the Mellin basis or the modified Mellin basis. But that's not the case in the case, but that is not what happens when you take the subleading soft limit. In the subleading soft limit, it turns out that is that basically that the subleading conformal soft graviton operator in Mellin in the standard conformal basis is slightly different from what you get in the modified Mellin basis, and the relationship between the two is basically the following equation. Okay. But for what I'm going to say next, in this case, actually, this distinction is not going to be very important for us. Okay, good. So now, as before, as we saw that the leading conformal soft theorem that was related to the word identity for super translations. So from this, let's try to see that what sort of symmetry does this word identity imply. Okay. So once again, what you can show is that basically this word identity or
one question.
Yeah, of course. Go ahead. Sure.
Yeah. So in the usual case, when we did when you try to relate soft theorems to word identities, one of the steps is that we say that okay, this is the symmetry of scattering, and so then we have to do antipodal matching and say that okay, this is the there's a PMS group on both the past and future null infinity, and then you have some kind of matching.
Yes.
So you don't need to do that here for the modified Mellin thing.
Yeah. So in this case, So basically, in this case, we are actually not doing that because implicitly I am not making any. Okay. So basically, in this case. Okay, so basically in this case I'm not making much of a distinction between incoming and outgoing particles. In this case, the only sort of label which distinguishes incoming and outgoing particles is basically this label epsilon. Okay, so in a sense I am working in sort of basis where you can consider, let's say, all particles to be either outgoing or incoming. But then the particles which are outgoing will have actually kind of positive energy, and the particles which are incoming will have negative energy.
Yeah, I understand that in the Mellin basis, but in the modified Mellin basis where you have an U, it seems to looks like future null infinity. That's where.
Oh yeah. Sorry. Oh yes. So in that case, So actually, it turns out that this guy, when you translate it back to the usual Mellin space, so then you get back these factors of epsilon actually, and that is because of the following. So here also, okay. So in all of these formulas, there is this extra factor of epsilon, which denotes whether the operator is incoming or outgoing. Okay, so which I have conveniently suppressed everywhere. But it turns out that if you go from this guy, I del del UK, O of epsilon, H bar, in the modified basis, that is related to epsilon k pk times O of epsilon hk bar of your zz bar. Okay. Yeah. So in this case, basically that is what happens actually. Yeah.
Nice.
Right. Yeah. So, or in other words, what you can think of is that basically you can think of only one time coordinate, but now depending on whether the particle is incoming or outgoing, you can yeah. So so an equivalent way of saying this is that for an incoming particle, you can replace the u's by v's, where the v will be some retarded time coordinate. Oh yeah, sorry. So yeah. So basically, in this case, where v will be some advanced time coordinate, and for outgoing particles, you use the label u. But that makes the formulas a bit more complicated. So yeah. So in order to condense everything.
Yeah, but that's inbuilt.
One compact form. Yeah, exactly.
That,
so
that
here
thing is inbuilt here.
Exactly.
Okay.
Exactly. So yeah. So that thing is inbuilt. Okay. Excellent. Yeah. So now, So now what I want to highlight is that what is the symmetry which this subleading conformal soft theorem actually gives us. Okay. Okay. So as before, as in the case of super translations, what you can do is that you can expand the subleading soft graviton operator in the following form. Okay, so it turns out that if you expand so basically if you expand this guy in terms of z bar, okay, so one assumption again which I swept under the rug is that here I'm assuming z and z bar to be actually independent variables, right? And that I'm implicitly assuming that I have gone to 2,2 signature now, where z and z bar are no longer actually complex conjugates of each other. And so therefore it makes sense to expand individually in z and z bar. So basically what I'm doing is that I'm just expanding this subleading soft operator in terms of z bar. And if you do that, then you basically get actually 3 sets of currents, which I have denoted here by J1, by J0, and by J minus 1. Okay, great. Right, and what you can show is that basically these currents have the following weights. They have the weights 1, minus a, and the point is that if you look at the word identity for these currents, then the word identity for these currents, so that takes the following form. Okay, where this L bar A is so these guys are nothing but your SL2C bar currents, which are basically the currents for the anti-holomorphic conformal transformations, which are given by L0 bar, L1 bar, and your L bar minus 1. Okay. So in this case, basically what happens is that basically, so now what happens is that basically this object or this word identity. So now this takes the form of some current algebra. Okay. And this current algebra, for obvious reasons now, I will call an SL2C bar current algebra, because this is sort of an affinization of the standard SL2C bar actually. So you can think of this as an affinization of the anti-holomorphic conformal group. Okay. So right. So now once again,
can I ask what exactly is an affinization?
Oh yes. So affinization is just a fancy name. So basically in this case, if that confuses you, you just look at basically this form of this word identity. Okay, and if you open any CFT textbook, then from there what you will immediately find is that basically the structure of this is basically what is known as a current algebra structure. Okay, and basically so in other words, to sort of say it in a simpler form, what these currents are going to do Okay, so right. So in this case, basically this cadence J of Z, what they are going to do is that they are going to implement actually local versions of your SL2C bar transformations. Okay, so imagine that you are doing an SL2C bar transformation independently at each point of actually Z and Z bar, right? And so in that sense, so in that sense, is cadence are generating in that sense, and actually local SL2C bar actually sort of transformations, and that and that has a fancy name that is known as affinization.
I see. Okay.
Okay, excellent. Right. So so then basically what you can do is that you can okay. So now also it is once again convenient to actually consider the modes of this cadence as we would do in standard 2D CFT. And what you can and if you compute the commutators of this cadence, then you will see that these commutators take the following form. And once again, if you open up your favorite 2D CFT textbook, then you will see that this is basically this commutation relation has the structure of a current algebra. Okay, but but in this case, the thing to note is that basically the level of this current algebra. So in this case, that is basically 0, or in other words, this is also related to the fact that the underlying central charge of this theory is also going to be 0. Okay, right. So this is what I just said, that this is so basically what you can show is that just from the okay, so just from your knowledge of how anti-holomorphic conformal generators act on conformal primaries, you can find out how this capital J of M's they act on conformal primaries as well, and that takes some simple form like this. Okay, excellent. So now, as before, what we saw is that basically the super translations. So basically the super translations had a geometric interpretation, in the sense that we saw that if you do a super translation, then so in that case the time coordinate with respect to null infinity, that gets shifted by an arbitrary function of your ZZ bar coordinates, right? But so similarly, one can sort of think of a geometric interpretation of this cadence as well, of this cadence J of Z, which you get from the subleading soft graviton theorem. And the interpretation here is the following: that you can think of this cadence as generating a certain class of diffeomorphisms on the celestial sphere at null infinity. And these diffeomorphisms basically take the following form. So if you do a transformation of the Z and Z bar coordinates, then the Z coordinate does not change, but the Z bar coordinate actually shifts by some function like this. Okay, where this A, Z, B, Z, and C, Z are some arbitrary functions of Z. Okay, good. Right. Right. So now let me also briefly mention another symmetry which follows from the subleading soft graviton theorem, and that is basically the Virasoro symmetry. And so this will connect to a question which actually one of you guys actually asked last time. Okay, so now it turns out that if you take this subleading conformal soft graviton operator, which was denoted by S1 Z comma Z bar, and if you do what is known as a shadow transform, which is basically some integral transform of the following form, then so now the point is that if you do this integral transform, which is the shadow transform, you can define some new set of operators, which I have denoted as T of Z, and by by T bar.
Excuse me.
Yes, Aditya, go ahead. Yes.
On the right hand side, what is S a function of? Is it supposed to be Z, or is it supposed to be?
Sorry. So thank you for pointing out all my typos. So this is again a typo. This has to be WW bar.
Thank you. Okay.
Excellent. Similarly here. Excellent. Yeah. Right. So yeah, so now basically by doing this integral transform, you can define a new set of operators, which I've denoted as T of Z and T bar of Z bar. And it turns out that if you insert this T, Z and or let's say T bar of Z bar inside some correlation function in the celestial CFT with some primary operators, then it takes the following form, which is the standard form of the stress tensor word identity in a 2D CFT. Okay. So from this, what we see is that basically these operators, this T of Z and this T bar of Z bar, which are shadow transforms of the subleading soft graviton operator. So these guys are basically generating, in this case, the Virasoro symmetry. Okay. Right. And so this is basic. So in this case, this is a general conjecture that basically if you take any quantum gravity S matrix, then any quantum gravity S matrix in 3+1 dimensions should actually have this Virasoro symmetry. Okay. And this is one actually kind of context of how we see that. Okay. Okay, so so I have not been very particular with the references all throughout this talk, but I just wanted to point out is that basically this construction of so in this case, basically this construction of actually the two-dimensional stress tensor by using this shadow transform of the subleading soft graviton operator was done first by Strominger and friends. And then but they did not put it in exactly in this Mellin space language. So that was later on done by actually Steiberger and collaborators in this paper, which appeared a couple of years ago. Okay.
Can I ask a question?
Yes, Anish, go ahead.
So if I take a shadow transform, it does not respect holomorphicity, is it? Like if I take the shadow of some holomorphic operator, will that shadow be holomorphic, or it need not be?
No. So in this case, the shadow will not be holomorphic, but in this case, so in this case, it turns out that if you take the shadow transform of the negative helicity soft graviton operator, then so which is denoted by this S1 minus. So that basically gives you the holomorphic stress tensor. And alternatively, if you take the shadow transform of, let's say, the positive helicity soft graviton operator, then that, so in that case, that gives you the anti-holomorphic stress tensor. Yeah.
I see.
But in this case, the point is that, as you said, is that basically these operators, this S1 plus and minus, they are not individually holomorphic operators. Yeah.
Right. And if I take a shadow of the stress tensor again, I should get back these S1 operators, right?
Yes, exactly. That's right. That's right. Yeah. Okay.
Excuse me, that last thing he said that if we take a shadow of the TZ itself, I get back the SS. Is that what the statement was?
Yeah. So in this case, you have to.
How would that work out? Because on the one hand, you have a function.
So in this case, you can take what is known as an inverse shadow transform.
Oh, I see. So it's not the same expression. It's like another expression that will do the opposite of this action, right?
Yeah, right. So in this case, what it turns out is that basically, if you do a general shadow transform, then the integral that you have, or basically these Z factors that you have, they look something like this. So they will look like something like this. For a general operator, which let's say has some dimension HH bar, the shadow transform involves some factor like this, and 2 minus 2H and 2 minus 2H bar times some operator WW bar, which has some dimension HH bar, and that gives you some operator on this hand, which is the shadow. Okay.
I see.
Yeah. So in this case, basically, so basically, when you do a shadow transform, this is the kernel that you have to use. Yeah. Okay, great. Yeah, so okay, great. So as of yet, I have been telling about actually various sorts of word identities and associated symmetries, which you can derive from actually the which you can derive by taking the limit. Yeah, so yes, so which you can derive. Yeah, so which you can derive by taking the soft graviton limit. But equivalently, you can so in this case, what you can do is that you can also consider other sort of massless particles, and the other natural massless particle to consider are of course and actually kind of photons or let's say gluons. So for example, in this case, if you let's say take so for example, if you consider, let's say, some scattering amplitude in, let's say, some non-abelian gauge theory, like let's say Yang-Mills, and so in that case also you can so in that case also you can take actually, let's say, the soft gluon limit, okay, and if you take, let's say, the leading soft gluon limit, where you take again this limit where you have, let's say, delta goes to 1. Then again, what you can show is that basically in the celestial CFT side, again, you basically get a word identity. And in this case, and in this case, the word identity, basically takes the form of a standard current algebra, which is basically some, so this basically takes the form of a, standard Cash-Moody current algebra. And it turns out it turns out that if you do this, let's say, for tree level amplitudes, then then the algebra that you get is basically is that basically you get so from there you get some algebra which looks like this, and once again, for the tree level amplitudes, what you find is that basically the level of this algebra, so that is again equal to 0.
But we expect that if loops are if we study loops as well, we'll get a expansion.
So for loops, actually, for gluons, the thing is actually this word identities have to be a bit more carefully stated, because what happens is that basically the gauge coupling runs. And so basically the gauge coupling in the IR runs, and also there are other issues. So for example, actually in the infrared, the gluons are not actually correct asymptotic states, right? Because for example, if if we take, for example, QCD, then in that case gluons are confined. So in this case, for gluons, this soft theorem sort of kind of makes sense only at tree level. But what you can do is that, for example, you can take the case of photons actually. So for photons, if you sort of do this, then also what you find is that at tree level, you find that the level is 0. Also at loop level, you find that the level is still 0. But at loop level, but there actually there is an interesting story which I will not be able to go into. So there is so in that case there is a story about a magnetic soft theorem. So so for photons there is an electric soft theorem and there is a magnetic soft theorem, and it turns out that actually both of them actually sort of give rise to actually some current algebras, and there is some off diagonal commutator which you can compute. So for example, you can compute so for example, you can compute the commutator of, let's say, the electric soft current and the commutator of, let's say, the magnetic soft current. Then that commutator actually has a non-zero level.
I see. Okay.
Right. Okay, great. So in this case, that is what we had for the so that is what we had for the leading conformal soft gluon theorem. So another interesting case to consider is the subleading conformal soft gluon theorem, which in this case takes, which again you can show takes the form of some word identity in the corresponding celestial CFT. And from this also, and this word identity also, if you sort of massage, then you can show that this also in that is that basically this leads to a set of two currents which are denoted by JA and by KA, so in this case also these yes, and the point is that if you actually look at the word identities for these corresponding currents, which you can derive so and of course which you can derive from this parent word identity. So in that case also what you see is that basically those word identities also take the form of some current algebras. However, in this case, there is an there is an interesting point about this subleading conformal soft gluon theorem, which is that basically, if you take these currents, which is this JA and this KA, and then you consider the modes of this, which is given by, let's say, JAM and KAM, where your M is some integer. But now if you try to compute, let's say, the commutators of these guys, then you will see that these commutators, they don't actually close. Okay. But what happens is that if you evaluate the action of these commutators on, let's say, some conformal primary, then what you can show is that basically the commutators actually close. So in a sense, this current algebra, which you get from the subleading conformal soft, which you get from the subleading conformal soft gluon theorem, is not a standard current algebra. Because of the fact that if you consider the modes of the currents which define this current algebra, then you see that so in that case you see that basically the modes of these currents, they don't close, but they do close in a sense when you act with these commutators on, let's say, some conformal primary operator. And so what one can say is that basically this current algebra is some non-standard current algebra which actually closes only on shell and actually not off shell. And by off shell I mean that when you compute the commutator in general and not evaluate it on some specific operator. Okay, so right. So in this case, this is a weird thing about this current algebra that you get. And this is actually so actually finally what is the status of this current algebra? This is actually still an open problem. It is not very clear that how one should actually think of this current algebra, because in familiar examples of 2D CFT, we never encountered we never sort of encountered such current algebras which close only on shell and not off shell. Okay, great. So so before sort of telling about a bit more about the operator product expansion in celestial CFT, let's just summarize what we have done so far. So basically what we have learned is that these conformal soft theorems can be interpreted as actually word identities in the celestial CFT. So for example, the leading conformal soft graviton theorem is a word identity for super translations. The subleading conformal soft graviton theorem, so from that you can get actually two sorts of symmetry algebras depending on what you do. So either you get an SL to C bar current algebra or you get an SL to C current algebra. And in this case, the distinction is due to the fact whether you take a positive helicity graviton soft or you take a negative helicity graviton soft. Okay. But then if you do, as we discussed, is that if you do a shadow transform of the subleading soft graviton operator, then what you can get from there are basically Virasoro word identities. Okay. And similarly, we can actually take, we can consider the soft limits for gluons or even in the case of photons. And in that case, for example, the leading conformal soft gluon theorem that gives rise to some Catch-Moody current algebra, and the subleading conformal soft gluon theorem that also leads to some quote-unquote current algebra, in the sense that this is slightly weird, in the sense that its generators don't close off shell. Okay. Okay. So are there any questions at this point?
Yeah, can I ask a question?
Of course, sure.
So in the case of the subleading soft graviton theorem, there is a way in which you can take the like a conformal dimension like you could get the shadow Virasoro to get some difference to symmetry also, right? Is there any? Is it of? Can you say something about that?
Oh yes, right. So in this case, are you asking about the geometric interpretation after taking the shadow?
Yes.
Oh yes, yes. Oh yeah. So in that case, the geometric interpretation is clear, right? Yeah. So in that case, what it is basically doing is that it is basically generating the standard Virasoro transformations, which we know, right? Yeah.
Right.
Yeah. So in that case, basically, once you do the shadow transform, then you basically get actually the standard sort of Virasoro generators, and we know what is the action, and we know what is the geometric action of Virasoro generators, right? I mean, for example, if you take let's say some ln's, where let's say n is some integer, then what you can define is that you can define actually vector fields which are of this form. Which take the following form: z to the power n plus 1 del z. You can similarly define L bar n as z bar n plus 1 del z bar, right? And and then if you compute, let's say, the algebra of these vector fields, then that basically gives you the so that basically gives you the standard actually Witt algebra.
Right. So what I was asking is this the recent paper by Andrea Pum in May of last year?
Okay, right. Oh, I see. Right. Yeah.
So there you take the shadow transform of Virasoro and you get this defect to symmetry.
Correct. Yeah. So basically, in that context, there was this sort of I mean, from the asymptotic symmetry literature point of view, I mean, there was this sort of this sort of debate about what is the interpretation of this as an asymptotic symmetry, right? So basically, when you discuss this asymptotic symmetry, you have to tell me how the vector fields for these symmetries, they act on the celestial sphere and so on.
Right.
So now when people ordinarily discuss this BMS symmetry, or even when if you see papers by actually kind of Barnich and others, where they discuss super rotations and so on. So in that case, they say that the kind of vector fields which you are allowed on the celestial sphere. So in that case, basically those vector fields have to have a certain form, in the sense that that these vector fields can't have any singularities on the celestial sphere.
Right.
But that is not the case. But that is not what we want from Virasoro, because in the case of Virasoro, we want actually so because in that case we want actually meromorphic actually sort of vector fields. So basically what Andrea Pum and what I guess Pastersky showed is so I think what they clarified is that basically what is the geometric interpretation when you do the shadow transform. Right. Yeah, but unfortunately, I don't actually have anything more sort of actually intelligent to say about that connection. Okay, excellent. Okay, so now I think I have I think I have 7 minutes. Okay, great. Okay, so let's say in this 7 minutes, let's try to see how all of this connects to all of this connects to some notion of operator product expansion in the celestial CFT. Okay, so as all okay, so basically as you guys all know,
you have 15 minutes, Sudip. Don't
I have 15 minutes.
Okay, yeah, we started late. So
okay, great, excellent. Okay, great. So as you guys know, that basically the operator product expansion is a very important tool which is So the operator product expansion is a very important tool in the study of actually conformal field theories, right? And so now what one can ask is that how does one study the operator product expansion in the case of celestial CFTs? Okay, so the first question which you may have is that basically what does the OP in the celestial CFT correspond to in the language of the scattering amplitude, or in other words, what do you have to do on the scattering amplitude side, which will give you something in the celestial CFT which looks like an OP. Okay, so it turns out that basically that the leading term in the operator product expansion in the celestial CFT is related to what are known as actually collinear singularities in scattering amplitudes. So in this case, basically collinear's limit of a scattering amplitude is basically a limit where, let's say, two external momentas, they become actually parallel to each other. Okay, and what you can show is that basically if you consider some scattering amplitude involving, let's say, massless particles, and then you take actually two momentas to become parallel to each other, then what you can show is that basically such amplitudes factorize in a certain way. Okay, so in order to see that, let's take another example. Okay, so let's consider some n graviton scattering amplitude, which we have denoted here as follows. There's some function of momentas pi's and some helicities sigma i's. And now we can consider the limit where, let's say, P1 becomes parallel to P2. Okay. So then if you look at how the dot product behaves of P1 and P2, in that case, you will see is that basically you get some factor of the following form. But now, as we were doing before, we can go to 2,2 signature, where Z and Z bar are independent are basically okay. So where Z and Z bar are actually independent quantities. In that case, what you can do is that you can take what is known as a holomorphic collinear limit, which means that you can take, in this case, Z12 going to 0, and what you can do is that as you take Z1 to 0, what you can do is that you can basically keep Z bar 1 to fixed. Okay, and so that is what is known so that is what is known as basically as the holomorphic collinear limit, because we are taking Z and Z bar to 0 independently. So then what you can show is that in this limit, if you have some graviton scattering amplitude, then that object basically factorizes in the following fashion. So an n+1 point amplitude, again, I have some typos here, sorry. Okay, so basically what you can show is that an n+1 point amplitude that breaks up into an n point amplitude. Okay, and there is some overall prefactor. This overall prefactor is what is known as the splitting function, and this turns out to be a universal object, in the sense that even if you add actual loop corrections, then the form of this object actually does not change. And that is because of the fact that this so-called splitting function is just determined by the 3-point vertices in your theory. And the 3-point vertices in this case are actually basically just fixed by symmetries. And so even if you include loop corrections, the form of the splitting function does not change. So so the splitting function looks has some particular form which looks like this in actually momentum space. Now so now what we can do is that we can take this form of the factorization of the amplitude in this collinear channel, and we can then do a Mellin transform of this guy. Okay, so if you do a Mellin transform, then what you get is an object of this kind. So you have an n-point Mellin amplitude, then that gets related to an n-1 point Mellin amplitude in the following fashion, where you have some leading coefficient which is given by some number, okay, which in this case is basically denoted by this factor. And then you have some factors of z bar which look like this. So you have factor of z bar 12 by z12. So notice that this object has a pole with respect to 1 over Z12. Okay, and this pole looks like and this structurally is sort of similar to actually something when you do an OP, because when you do an OP, in that case also you get and actually some pole structure when you, let's suppose, consider the leading term in the OP, right? So okay, so now it turns out that this object, yeah, so basically this overall number which we had is basically some product of gamma functions, and this is known as the Euler beta function. Okay. So okay, so now the basic statement is the following: that this factorization of the Mellin amplitude, which we saw in the collinear limit, so that can be interpreted as an OPE factorization. And since you notice that this factorization does not care about what the other particles in the amplitude were, right? So in this case, the only objects that are relevant for this factorization are the data of the particles whose moment I have been taking collinear, right? So then from this amplitude statement, what you can show, what we can say is that basically we can extract the following operator statement from it. Okay, and what we can say is that basically that there is an operator statement of the following form, which says that if I take let's say two graviton operators denoted by, let's say, G1 and by G2, and I take their OP, which is basically Z12 going to 0, then I get some structure. Okay, so then I get some structure which looks like this, and this essentially gives me the leading term in the celestial OP. Okay, right. So yeah, so basically in this case, it turns out that if you take the OP between two graviton primary operators on the celestial sphere, then in that case yeah, so basically in that case you get some object which looks like this. Okay, great.
Excuse me,
So,
I just
yeah.
wanted to ask,
yes,
the exponents of Z12 and Z12 bar are opposite.
Yes, yes, yeah. So
can you see how does that match with with the scaling weights of the objects on the two sides?
Okay, good. Yeah. So in this case, yeah. So in this case, basically the scaling weight actually simply matches because you see that on this hand you have actually delta 1 and you have delta 2, and the graviton operator which appears here that has dimension delta 1 plus delta 2. Now, okay, so and now this is some dimensionless object, right? Because Z bar has dimension -1, 1 by Z has, and 1 by Z has dimension 1, right? Okay. So this is some dimensionless.
Okay.
Good. Okay. So now let me make a few comments. Okay. So now we have been okay. So now the point is that we have been talking about all these symmetries, all these infinite dimensional symmetries, which follow from various soft factorization theorems in the celestial CFT. And it turns out that these asymptotic symmetries or infinite dimensional symmetries, they actually highly constrain the form of this operator product expansion. Okay. So for example, in a very nice paper a couple of years ago, what was shown is that basically if you consider this leading structure of the OP, then in that case this lead so basically in that case this number which you can think of as the leading OP coefficient, this number is completely determined by asymptotic symmetries. And in this paper in this case by Strominger and collaborators, what was shown is that this leading OP coefficient, for example, in the case of Einstein-Yang-Mills theory, so that object can be completely fixed by symmetries, and the symmetries which they used were actually some global symmetries, and these global symmetries were associated to the subleading so in this case these global symmetries were associated to the subleading soft gluon theorem in the case of gluons, and and to sub-leading soft graviton theorems in the case of gravitons. Okay. Yeah. So actually motivated by their paper, what I and actually Shamik wanted to do is that basically we wanted to understand. So now we wanted to understand actually two sort of questions, and the first question was the following: is that basically what is the structure of the subleading terms in this OP? So of course, from this we just learned that the leading term in the OP is basically equivalent to the so basically in this case the leading term in the OP is basically equivalent to actually the leading collinear limit. But now if you really want to study the okay, so now if the OP really makes sense, if there is actually a notion of an operator product expansion on the celestial CFT, then we should also be able to, so in that case we should also be able to make sense of the subleading terms in the OP. Okay, and therefore it is important to understand what the subleading terms look like and how the symmetries dictate actually the structure of the subleading terms. Okay. So then the point is that we tried to study that problem, and basically what we found is that basically in certain cases, for example, in a very special case, which is which is the case of tree-level MHV graviton scattering amplitudes. So in this case, basically what we showed is that if you consider, let's say, tree-level scattering amplitudes, or rather a particular class of tree-level scattering amplitudes, which are known as these MHV scattering amplitudes, in either in Einstein gravity or in the case of POD angles theory, then it turns out that the celestial OP between, let's say, either two gravitons or between two gluons, that can be completely determined using the underlying infinite dimensional symmetries. Okay, right. So in this case, what do I mean by completely determined? So basically, what Strominger and collaborators showed is that basically in this OP, from asymptotic symmetries, what you can determine, or the particular asymptotic symmetries which actually they considered, what they showed is that you can determine the leading OP coefficient. Okay, but what they had to assume is that the structure is that basically the exponents of this Z and Z bar are basically given by this. Okay, so they had to assume that the exponent of Z bar is basically equal to 1, and the exponent of Z is basically this and they had to assume that the exponent of Z is actually given by -1. Okay, but it turns out that in the case of MHV scattering amplitudes at tree level, you can actually do more. It turns out that the underlying symmetries which govern the sector of MHV scattering amplitudes are actually so constraining that they even determine. So it turns out that they are so constraining that these symmetries not only determine what this leading OP coefficient is, but they also determine what these exponents of actually Z and Z bar can be. Okay, so in that sense, the celestial OP is completely determined by the underlying symmetries in the MHV sector. Okay, so I don't have time to actually sort of go into the details of how that happens, but let me just tell you actually sort of quickly what is the essential story behind it. Okay, so in this case, what happens is that what you can show is that basically the symmetry algebras which we discussed, that follow from the various soft theorems, it turns out that the symmetry algebras admit certain null states. Okay, and what you can show is that basically this null states, these null states have to decouple when you insert them within, let's say, some physical scattering amplitude, and then the statement of this decoupling can be basically translated into a differential equation. And it turns out that the decoupling of this particular null states, they actually give you a set of partial differential equations, which this MHV amplitudes either in Einstein gravity or, let's say, in the case of periodic angles, they have to satisfy. And what turns out, so for example, let me just show you what these differential equations look like. So for example, in the case of, let's say, graviton scattering amplitudes, if you take any endpoint, let's suppose graviton MHV scattering amplitude in Einstein gravity at tree level, and you do the Mellin transform of it, then what turns out is that this Mellin transformed amplitude obeys a first order partial actually differential equation, which actually looks like this, where so in this case, where these guys are actually basically some differential operators whose form is not going to be very important for now. So let's skip over that. And then in the case of gravity, we also, what we find is that there is also another actually partial differential equation, which turns out to be very important, which also follows from the decoupling of a particular null state. And that takes form, and that takes some form like this. Okay, great. So now the essential point is that these partial differential equations, they completely determine the leading OP between gravitons in the following sense. So what you can do is that you can start out with an ansatz for the OP. So you can assume that you can start with an assumption that the OP takes some general form like this, where so now what you can do is that you can basically insert this ansatz into this differential equations which I showed you. And then what you can do is that you can basically expand out all terms in the differential equation in powers of z bar. And then what you can do is that you can basically match the similar powers of z bar from both sides. Okay. So so basically, if you employ that strategy, then what you will find is that you will find certain recursion relations for these OP coefficients, which which in this case turn out to look like this. And it turns out that these recursion relations for this leading OP coefficients have a non-trivial solution if and only if in this case these exponents p and q, which were the exponents of recall z12 and z bar 12 in the OP, they take the following form. So basically these recursion relations are actually mutually consistent if and only if p is equal to -1 and q is equal to 1. And this is precisely what you get if you do an explicit computation of the collinear limit of the scattering amplitude and then take the Mellin transform and so on. Okay, and then consequently what you can show is that basically with these values of p equal to 1 and q equal to p equal to -1 and q equal to 1, you can solve these recursion relations, and basically solving the recursion relation that actually uniquely determines for you in this case the leading OP coefficient, which is given by this. And it is not a surprise that this object also matches the answer that you would expect from an explicit calculation of the scattering amplitude. Okay, so in that sense, the leading structure of the OP is completely determined by symmetries. It turns out that so now it turns out that the subleading terms are also completely fixed. It is a bit laborious to actually compute all the subleading terms, but what you can show is that there is a systematic procedure for actually computing all the subleading terms in the OP. And what you have to do is that you just have to impose, in this case, you just have to demand that the OP is invariant under all the infinite, all the sort of relevant, in this case, infinite dimensional symmetries of the system which you are studying. And it turns out that so basically in this case it turns out that if you impose invariance of the OP under all these infinite dimensional symmetries, then from there, yeah, so basically from there, and actually once again, what you can show is that basically you can get some recursion relations, and these recursion relations once again basically fix for you what the subleading OP coefficients are, or in this case, the subleading OP coefficients basically mean the OP coefficients for descendants. And by solving these recursion relations, what you can show is that basically basically the OP coefficients for the descendants are all basically fixed in terms of the OP coefficient for the leading primary. And so that is some story which which should also be familiar from the study of 2D CFTs, because in the standard 2D CFT case also, if somebody tells you what the leading OP coefficient is, then by using the Virasoro symmetry, you can determine all the subleading OP coefficients as well. But in this case, what turns out to be useful is that in this case, so basically in this case, what turns out is that to characterize the subleading terms in the OP, it turns out that actually Virasoro is not very useful. What is more useful in the case of gravity is basically this SL2C bar current algebra and super translations. And what you can show is that basically all subleading terms in the OP, they fall in representations of this SL2C bar current algebra and super translations. And so once you specify this algebra and how they act on primary operators, you can determine all the OP coefficients from it. Okay, good. So the last thing that I want to mention just in a few seconds is that basically there are similar results which you can which you can derive for the case of gluon amplitudes, for the case of gluon MHV amplitudes in Yang-Mills theory as well. And in that case also one also gets interesting differential equations from the decoupling of null states. And in this case one class of differential equations that you get are basically are basically equations which resemble the so-called Nishnik-Zamolodchikov equations in two-dimensional CFTs, which have some underlying current algebra symmetry. The only thing which I want to point out here is that basically this equation has some structural similarity with actually Nishnik-Zamolodchikov equations, but it is not exactly the same, because if you take a standard Nishnik-Zamolodchikov equation, then that object only contains these first two terms, but the differential equations in our case, they also contain an additional piece, and it turns out that this additional piece has to do with actually the subleading soft gluon theorem, and it is because of the fact that your scattering amplitude satisfy the subleading soft gluon theorem, you need to have this extra piece. Otherwise, so in this case, you need to have this extra piece. Okay, great. So that's what I wanted to say about gluons. Okay, so let me just close by making a few comments. Okay, so essentially, it turns out that these infinite dimensional symmetries, they allow you to completely solve for the scattering amplitude in the MHV sector, at least in the simple case in the MHV sector, in a bootstrap sense. And that I'm saying, so because so in this case I'm saying in a bootstrap sense, because essentially what these symmetries allow you to do is that they completely fix the structure of the operator product expansion for you, right? And which means that you so in this case basically it fixes completely the structure of the OP, and so even the leading OP coefficient is fixed, the subleading OP coefficients are fixed and all that. And so therefore, essentially, it determines for you all the data that you would need in principle to compute the scattering amplitude. Okay, so in that sense, in a bootstrap sense, these infinite dimensional symmetries allow us to completely solve for the MHV sector, at least at tree level. Okay, and what you can say is that you can also actually drape some more fancy words around this, and the fancy words go as follows, which is that and so the fancy word squared follows is that from this what this sort of hints at is that this hints at the existence of a minimal model like actually decoupled sector in the dual celestial CFT. And here I'm saying minimal model like in the sense that this sector is completely solvable. And it is decoupled in the sense that that this is solvable and it is completely determined by a certain class of symmetries. And it turns out that, and what you can say is that this decoupled sector in the celestial CFT provides a complete holographic description of actually tree-level MHV gravity, MHV scattering amplitudes in Einstein gravity and in the case of POD angles. Okay, so in this case, so basically what this amounts to is that basically you can abstractly define so basically what this turns out is that in a sense you can abstractly sort of specify what the symmetries of your theory are, and you can and there is a certain class of symmetries which single out a certain specific sector in the celestial CFT, and this sector is completely solvable. It actually holographically solves for you the set of MHV scattering amplitudes in Einstein gravity and in POD angles theory. Okay, so in this case, that is all I had to say, guys. So actually, thank you very much in this case for your attention. Okay, so so with that, I will actually stop.
That's all. Thanks, Sudip, for the excellent set of lectures.
So in this case, if you have any question, then if you have any question, then I will be happy to take them.
Yeah, if anyone has any questions, please ask.
Yeah, so actually this last part went a bit fast. I apologize for that.
I think did Anish unmute himself?
No, I was about to say exactly the same thing. The last part went a bit over my head. So
That's okay. I mean, if you could share your these handwritten notes on Slack, that would be.
Yes. So actually that I will. So that let me do actually. So that I will do.
Great. Also, like Sudip, like since we had at the start of the talk planned to sort of like discuss a little bit, maybe if others are interested, like Anish and Manu, if any of these guys are interested, they can also join. Like
of course, yeah, sure, definitely.
When is the
Yeah, we haven't decided yet, but like we'll figure it out at some point.
Yeah,
sure.
Yeah.
Okay, but are there any other questions for now?
I think I would have to read all that stuff to be able to ask more things. So if you could share, and hopefully we can reach out to you afterwards as well to ask something.
Sure. Yeah, so I will put up these notes on Slack.
Cool. Okay, so if there are no further questions, then let's thank Sudip again.